Question 4, part 2 is chi-squared calculations. One of the F1 was back-crossed with a double homozygous recessive. Wow, what's that even mean? Back-crossed or a test cross. Double homozygous recessive, we should be okay. Homozygous recessive, so little t's, little a's. And the F1, if you remember, go back to the F1, that was heterozygous. And I'm not going to draw a diagram to show this, but you would expect this 1-to-1-to-1 ratio if you do that, because there's half of them have got a big T and a little t, and half of them have got a little t and a little t, and likewise with the A's. So you would expect that. These are the numbers that they actually found. Those don't look like 1-to-1-to-1-to-1 ratio, do they? And incidentally, it doesn't actually have it in this question, but that you got more that look like the original the parents or the parental types. So you'd suggest gene linkage here as the explanation for it. However, use the chi-squared test. So hopefully you are going to be okay with this. Right, so they've started the table. The table's got enough holes in it, cells in it. First thing we need to do is find our total. 24 plus 10 plus 13, 40 plus 25, 72. Expected, well, that's our 1-to-1-to-1 ratio there. So 72 divided by 4. If it was 1-to-1-to-1 ratio, we would expect all of them to be 18, and that would add up to our 72 of our total. Our columns here, well, we want O minus E squared, and O minus E squared, all divided by E. So we just need to bash through these. You do these ones in head. So 18, O minus E, 24 minus 18, that's 6. 10 minus 18, that's minus 8. 13 minus 18 is minus 5. 25 minus 18 is 7. When you're timesing these by themselves, the minuses disappear. So if you can remember your times table, 6 times 6 is 36, 8 times 8 is 64, 5 times 5 is 25, 7 times 7 is 49. You might need your calculator for this next bit. Divided by E, so 36 divided by 18. Well, that one's alright, that one's 2. 64 divided by 18, sorry, I'm going to have to go to the calculator now. So 64 divided by 18, that is 3. How many decimal places should we have? 3. So let's go for 3. 5, round up to 6. This will be zeros there. 25 divided by 18, 1.38, let's round that 9, so we've now got crazy numbers. 49 divided by 18 is 2.722. We are adding those up, so 2 plus 3.556 plus 1.389 plus 2.722 is 9.667. 9.667. And you know, how many decimal places? How many decimal places? Let's just do it to 2 decimal places, maybe 9.67. And I've just thought of a question that I did earlier on that required something in standard form that I didn't do. Haha. So I'm going to have to go back and correct that. But no, that's why you only need, 71% for an A star. You can make small mistakes. Right, use your calculations. Use your calculations and the probability table to conclude whether you accept or reject the null hypothesis. So, we need to go, how many degrees of freedom are we using? It's the number of classes minus 1. So, number of classes is 4, so we're going to use 3. And we always use the same level of confidence. So, confidence 0.05 or 5% confidence. When we do that, we get to 7.82. And the way I remember it is if the chi-squared is bigger than the critical value, then we can reject the null hypothesis. Chi-squared is bigger than our critical value. So here we go. So critical value equals 7.82, and that's going to get you a mark. And chi-squared is greater than the critical value, so reject null hypothesis. So are these numbers just, randomly slightly different to each other, or is there a significant difference between these numbers? And we're going, there is a significant difference, which we guessed at the start. So there is a significant difference. No, at 95% confidence. In the mark scheme it says 0.05%, which isn't right. You can't have 0.05 and percent. It's either 5% or 0.05 probability as a fraction of 1. The deviation from these numbers is not due to chance. There's something going on. So deviation is not due to chance. Right, here we go. They are asking for an explanation as to what's going on, and we suggested at the start this was due to gene linkage. So, with the use of annotated diagrams. So this is slightly tricky. So here's, if we make these pretty simple. So we've got there's our homologous chromosomes. And remember, you've got 2 copies of every gene. So the F1 plant. So the F1 plant was big T, little t, big A, little a. And it could give rise to 4 different gametes. So the key to success here is that we've got T and A on one of the homologous chromosomes, and on the other one it would be little t and little a. Little t and little a. There we are. And why are these kind of cross-shaped? Because the DNA is replicated. So if the DNA replicates, then these have also got the identical alleles. Okay. And then what could happen? So what could happen, that's kind of number 1, we could get crossing over. So these ones here kind of cross over but where would they cross over? If we cross these entire ones over, then it wouldn't be a difference, but they've got to cross over in between. So let's see if we can draw that. So let's draw these. There's our first one, there's our second one. So our first one is still the same, our last one is still the same, and this has still got its little T there, but these other ones are swapped round. So now got, so these are kind of swapped over now, and then when they separate off and go their different ways, these are still the same, but now we can see crossing over has happened. So we can see that these are now the other way around for these two, and that would give us our recombinant anthers. 15 marks, a lot of work for that last section.